In this video, what we're going to look at is using Maclaurin expansions to approximate values of functions at set values of x to a given accuracy in a given number of decimal places, because this is a vital application of being able to use the Maclaurin expansion with functions. There's no point in doing it if we can't use it. Now, what we want to do is evaluate any given function to a set amount of values in a given number of terms, so decimal places, or using the first four non-zero terms, for example, of the Maclaurin expansion, for any given value of x. Now, obviously, dependent upon the function, the value of x we choose may have limitations. For example, trig functions, sine and cosine. The value of x may have certain limitations on it, but we have to take that into account when we think of the value of x we select for the function. Now, the accuracy that we are after can be varied using more or less terms in the expansion. So if we went up to x cubed, we would have less accuracy than if we went up to x to the power of 5. We'd bring in more decimal places with that second expansion than the first one. We can judge how many terms to use depending on several key facts and factors within the function. So the first thing is that we have to remember that all series examined must be convergent in some region of validity. So if we think back to when we did power series and looking at limitations on x so that the power series itself converged to a value, we have to bear that in mind. This will only work if we choose a valid value of x for which the series will be expanded and then converge to a point. If it doesn't, this will not work. We also have to ensure that every term is less than the previous in the sequence, so something which is necessary for convergence. So for example, if my x cubed term has 4 decimal places, my x to the 4 term may have 5 decimal places or 6 decimal places before we get our first number. So we're getting smaller and smaller and smaller values, they're getting less, and we will eventually converge to some overall value for the sequence. And when the series is an alternating series, so think for example cosine or sine, the actual value lies in a region between two consecutive partial sums. So for example, if we think back to the cosine and sine, when we were doing that before, we'd have 1 and negative 1. So if we were having an alternating series that was going up and down, eventually what would happen for the given value of x is it would alternate up and down until it became almost flat and converged to some value that is within the middle of those two consecutive partial sums. And they would get closer and closer and closer, so the difference would eventually become minimal and infinitely small. So let's look at a couple of ways that we can do this, and just a couple of examples. You'll see exactly what I mean when we do this. So first example, let's imagine we want to find sine of 0.5 to 4 decimal places. Now what we have to first do is make sure we expand sine using the Maclaurin expansion of it. Well, sine of x, the Maclaurin expansion of that is x over 1 factorial, take away x cubed over 3 factorial, plus x to the 5 over 5 factorial, take away x to the 7 over 7 factorial, plus x to the 9 over 9 factorial, and so on and so forth. So it continues on after that. Now, there's no point in us continuing to calculate every single value, because essentially what it wants me to do is say that sine of 0.5 can be given by 0.5 over 1 factorial, take away 0.5 cubed over 3 factorial, plus 0.5 to the power of 5 over 5 factorial, take away 0.5 to the power of 7 over 7 factorial, plus 0.5 to the power of 9 over 9 factorial, and then so on after that. Now that's a hell of a lot of calculations to do, but what we could do is if we looked at 0.5 to the power of 7 over 7 factorial, what we would find is that that is equal to 0.0000 0, 1. And if we then rounded that to 5 decimal places, that would be 0. So what that means is if we are rounding it to 4 decimal places, our overall answer, as asked in the question, this here is not going to contribute to it at all. So we can then say, well, all I need to do then is this first 3 terms. Everything after that is going to have no impact on the 4 decimal places I want, so I don't actually have to physically calculate it. So it saves us a bit of work within our calculation. I can then just go through all of these, plugging them into a calculator and seeing what I get. And I'd then be able to say that sine is 0.5. If I do each term on its own, I get 0.5, take away 0.02083, plus 0.00026, and then I can stop at that point. We've already proven we don't need that one there. What I can then do is add it all together and round it to 4 decimal places, and I'd get 0.4794 to my 4 decimal places. And we could double check that with a calculator. Beyond that, it might be slightly different in terms of decimal places when we stick it in the calculator, but this would be a good enough approximation for us to use in a calculation later on. Remember this stage though. This is something that's actually quite good, because if we can get to a point where we can eliminate some of the calculations to do, it just makes our life a heck of a lot easier. Let's look at this example now. So e to the power of 0.5 to 3 decimal places. This is what we want to calculate here. Well, what we can remember from the previous set of work that we did is that e to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial, and it then continues on and on and on beyond that. So what this wants us to do is essentially and say e to the 0.5 is equal to 1 plus 0.5 over 1 factorial plus 0.5 squared over 2 factorial plus 0.5 cubed over 3 factorial plus 0.5 to the 4 over 4 factorial, then plus 0.5 to the power of 5 over 5 factorial, and then it continues on after that. Well, if we use the same sort of logic as we did before, if we look at this term here, the 0.5 to the power of 5 over 5 factorial, what that equals is 0.00026, and then it continues on. Now that is just equal to 0 to 3 decimal places. So this term and beyond is going to contribute nothing to what we want as an overall answer. It's going to do a little bit to the rounding, but anything beyond this isn't really going to contribute anything at all. So what we can say is, right, we can then cut it off at that point. We don't have to go beyond that. Still 5 terms, which is great fun, but we don't have to then do x to the 6, x to the 7, x to the 8, etc. So what we can do is then say, right, so to get e to the 0.5, all we have to do is 1 plus 0.5 over 1 factorial plus 0.5 squared over 2 factorial plus 0.5 cubed over 3 factorial plus 0.5 to the power of 4 over 4 factorial, then plus 0.5 to the power of 5 over 5 factorial. So if we calculate all of that together and then round it to 3 decimal places, we get the answer that we're after. And all you need to do is, if you plug all of that into a calculator, we get the answer of 1.649 to 3 decimal places. So the Maclaurin expansion is very useful in terms of helping us to give approximations of certain functions to certain values. Remember this step here though as well. We want to do as little calculation as possible, particularly with such complex functions that are going to be involved. So look at a point where you can cut it off and say to yourself, I don't have to do anything else beyond this. I'm just going to stop my calculation there and make my life a heck of a lot easier. So bear all that in mind when you're working these through.